Hello and welcome to this NEP for sigma notation. That's notes, examples and practice questions for sigma notation. So that's your title. So if you take your notebooks or your folders, wherever you're writing these notes, your title is sigma notation. And then we're going to be moving on to the notes section. So arithmetic and geometric series can be described using sigma notation. Now sigma notation is what the name of this Greek letter is, and it is how we can convey certain things about a sequence. Now, sigma means sum, and so what this means is we are doing the sum of this sequence here. Now, these bits here tell you r equals 1, that means we start at 1, and we go for 5 terms to the 5th term. So we have first term, second term, third term, fourth term, 5th term, and because it is the sigma, we're adding them up. So whatever we get for our answer, that is the answer itself. Contrary to that, we have a second sigma notation here, which we're still summing, and we've got the same sequence. However, in this case, it starts with r equals 3, so it actually starts with, over here, we had the first term, second term, third term, and so on. So what we can see from this sum here is that we are only we're only looking at the third term, and we're still continuing up to that 5th term there. So that's what the sigma tells us, and we will summarise that in just a moment. Now, what it says here, this is what you need to do. So you need to generate at least enough terms to find A and D or R. Then you can use the standard sum formulae for arithmetic and geometric series. And then the little blue box just says here, pay careful attention to the limits. You may need to subtract one sum from another. So essentially what we have is this means sum, and then this number here is the first term, and this number here is the last term. So we'll look at some examples of that in a moment. So they're your notes, then we're going to move on to the examples. So little subheading examples, and then example number 1, we have calculate 1a, and then we have this sum here. So we have sigma, that means we are summing something, and we are going from r equals 1 to 10. So remember, that was the first term, and that is the last term. Now, the way we need to do this is we need to generate at least a few terms of the sequence, and the sequence is here. So we are going to generate the first couple of terms. So term 1, term 2, term 3. So term 1 is 6 minus n equals 1, 6 minus n equals 2, 6 minus n equals 3, and so on. And what that does is that tells us the information that we're going to need. So a equals 5. This is an arithmetic sequence. It's going down in by subtracting 1. So d equals minus 1. The number of terms is 10 because that is my last term. And so I'm looking for the sum of the first 10 terms. So sigma tells me it's the sum from 1 to 10. So my sum formula for an arithmetic series is given in the formula booklet, like so. So subbing into that with the information from our box. And then I'm going to put all of that in my calculator. So that equals 5. And this is actually really easy to check because on your calculator, in the very top right, there is a button which looks like this. So what you want to put in your calculator is shift, and then it's the x, gives you this. Then inside the bracket, you're going to put 6 minus, and we're going to put x there because that's what our calculator deals in. X equals 1, and then 10. So put all of that in your calculator, just putting it in mine now, gives me 5. Perfect. Okay, moving on to question B. Okay, so we're still doing the sum here, so we've still got that sigma notation. And this time we've got n equals 1 and 7. Now again, the first thing we're going to do is we're going to generate the first couple of terms. So when n equals 1, that equals 4. If n equals 2, that's 8. And if n equals 3, that's 16. So we can see here that this is a geometric sequence, and therefore we can fill in accordingly. So again, we're going to put our information in a box. So a equals 4, r equals 2, n equals 7, and we're looking for the sum to 7. Now the sum to 7 is a geometric series. The formula for this is given in the formula booklet. Remember, there's 2 options for this. So the sum to 7 equals a 1 minus r to the n over 1 minus r. That all goes in your calculator, and that is 508. And again, we can check that using the sigma button. So inside the sigma, we're going to put 2 to the 2. So 2 times 2 to the x equals 1, and then 7 gives us 508. Okay, question 2. Write the following series in sigma notation. So sigma notation is always going to start with the sigma here and here. Now, the sigma notation, the next thing we have is we have the number of terms. So this has 1, 2, 3, 4, 5, 6 terms. So we can assume that that starts at 1 and goes to 6. And this one goes to 5. Now, what I need to work out is I need to work out the formula that's going to go inside my sigma notation. So this is an arithmetic progression. It's going up in 3s. So my formula is un equals a plus n minus 1 d, which we learned when we did arithmetic sequence. So a plus, and actually we can leave this as n minus 1, and then d is 3, and that actually is my general formula. Now what I can do is I can actually check this as well by adding these up. So if I add those up, just in my calculator, that gives me 63. And then if I put all of this in my calculator in my sigma button, so shift x, 3 plus x minus 1, lots of 3, from 1 to 6 is 63. So that is therefore correct. B is a geometric, so the nth term for a geometric is a r n minus 1. So a is 1024. R we can achieve or find by doing u2 divided by u1. So that is a half. So a r n minus 1. And again, I can check that in the same way by just adding up those numbers in my sequence. So that's 1984. And then if I put this in the sigma button, 1024 times a half to the power of x minus 1 between 1 and 5. Brilliant. Okay, final question, question 3. This is the stretch question. Now, it says, by considering the sum of the first 30 terms and the sum of the first 8 terms, calculate this sum here. So it's sigma, but this time we are going from 9 to 30. So imagine I had everything out in my all of my terms here, I'd actually be starting at the 9th term. So 1, 2, 3, 4, 6, 7, 8, 9, 10, 11, and so on. I would be starting at my 9th term. Now what that therefore means is that the sum from 9 to 30 equals the sum from 1 to 30, so that's the whole sequence, minus these terms here, so minus the sum from 1 to 8. And that's why the question tells us as the clue, considering the sum of the first 30 terms and the sum of the first 8 terms. Now that's a rule that we need to remember, and it's really important that we understand why we're only going to 8 on this one and not 9. And that is because my sequence itself starts from 9 and goes upwards. Now to find those sums, we still need to do the same as usual. So we need to generate the first couple of terms. So 12 times 0.9 to the 1, 0.9 squared, and 0.9 cubed. Now, because we are multiplying by 0.9 each time, that actually tells us what our common ratio is. However, there's no harm in generating it, because we still need to generate to get that first term. The first term is not 12, it is 10.8. So R equals, which is 0.9, n, and we're going to do this twice. So the first one we're going to do n to 8, and the second one we're going to do n to 30. And we are looking at the sum. And this is a sum of a geometric series, so we have our formula given in the formula booklet. So the sum to 8 terms is a 1 minus r to the n and that is 61.5095 ... And then we are going to do the sum to 30. So the same formula, but n has changed to 30. And that is 103.42. So therefore, my overall sum, so the sum of 9 to 30 is my sum of 30 minus the sum to 8. So I can put that in my calculator again, and that gives me 41.912 something. And I can check that by putting all of this in my sum function on my calculator, my sigma function up there. So to the power of x, and we go from x equals 9 to x equals 30, which is what we've got. So that's the crucial part there about considering the limits really carefully. So as a summary, we need to generate the first few terms to find A, D, and R. We can check using the sigma function on the calculator, which is in the top right. And we need to consider the limits carefully. Calculating two sums if required. So that's the summary. I'm going to put a red box around it, as always. We want that to go at the bottom of the notes, nice and neat, and that is just helping you going forward to think about those really key points, okay? So write that down, make it nice and clear, and then we're going to move on to the practice questions. Okay, so here are the practice questions for sigma notation. Okay, so we have the sum from 1 to 5. So start by generating the first couple of terms. And then we can calculate our sum. So A equals 8, D equals 3, N equals 5, because we've got 5 terms, so we're looking for the sum to 5. Now this is a arithmetic progression, and remember the formula for that is given in the formula booklet. All goes in your calculator, and that is 70, and then you can check that by putting this in the sigma function, and that is correct. Okay, for B, we have the sum from 1 to 12. So we're going to generate the first few terms. Which gives us the information for our box. This one's a geometric with a common ratio of 2, and n is 12. And we are finding the sum of 12. So the geometric formula is given. Put that all in your calculator. Which is 24570. And then again you can check that using the sigma function by putting all of that in the calculator screen. Okay, this one here is slightly different. We are still doing a sum. We're doing it from 1 to 100. And we have our sequence here. Now, if we generate our first few terms, we actually get 1, 1, and 1. Because 1 doesn't change. There is no r, there is no x, there's no variable. So that doesn't change. So you could use the box. So A equals 1, D equals 0, N equals 100, and you could use the formula for the sum to 100. It's a arithmetic progression, and what you will find if you do this is you will get 100. And the reason for that is because actually what you're doing is you're adding up 1 100 times. So that is correct. You could just do that without using the formula because you know how that's going to work. Okay, question B, evaluate. We have sigma, the sum, and this time we're going between 10 and 20. So what that means is to get from 10 to 20, we need to do the sum of 1 to 20 minus the sum of 1 to 9, because remember it starts at 10. So we'll generate our first few terms. And in our box, we have 2 lots of n this time. We have n equals 9 and n equals 20. So the sum to 9 using the information, it gives you 207, and then the sum to 20 is the same formula. And that gives you 1010. So the total sum is 1010 minus 207, which is 803. You can check by putting that in your calculator, and that will give you 803. Okay, final question. We have a sum, but it goes from 1 to k. Now here's my sequence, but actually it tells me the sum is that and says find the value of k. So the first thing I'm going to do is I'm still going to generate the first few terms of my sequence. This is actually the same sequence from B. And I can still use my box in quite a useful way. So A equals 3, D equals 5, N we don't know. But actually what we do know is we do know that the sum to k is this. So as normal, we can set up a series. We can set up a sum formula for the sum to k. So that's n over 2, 2a plus n minus 1 d. And that all equals 1575. So to simplify that, the first thing I'm going to do is times by 2, and then I'm going to simplify what's inside the bracket. So k, and then I've got 6 plus 5k minus 5 equals 3150. Expanding again, I've got 6 minus 5 is 1, so I'm going to have k plus 5k squared is this. Now that's a quadratic, so I can put it in my calculator, and it gives me k equals 25, or minus 25.2. Now k must be bigger than 0, so therefore k equals 25. And you can check that really easily just by putting in there and putting k as 25. So 5x minus 2 from 1 to 25 is that. So that is correct. So there you have it, sigma notation. Just be really careful with those limits, and if you need to, just write out more terms of the sequence until you can work that out.